Okay, good afternoon, everybody. So I'm Roland Trautner from the European Space Agency. It's a pleasure today for me to talk about our line of mass spectrometer developments. And I'm doing that on behalf of not only my ESO colleagues, but also colleagues from academia and industry, notably Open University, RAL Space, Kaiser Italia in Italy, and then our academic, our partners at NASA and at JAXA. Let's see if I get this. So this is what I'm going to talk about. I'll summarize the science goals and heritage of these instruments. Then I'll talk briefly about the instrument developments for PROSPECT in PROSPER and EMS-LUPEX, basically our spectrometer that we provided for PITMS. And then I'll talk in a little bit more detail about future incarnation of the instrument that we're developing for a flight with our partners in Japan with JAXA. And then I'll basically wrap it up in just a few words to be added on future flight opportunities. So the EMS science goals include assessment of the volatile components of the lunar exosphere, of the lunar regolith and exosphere, and observe the behavior from dawn to dusk, so over the diurnal cycle. We want to quantify the key constituents of the lunar exosphere, like water, methane, and a number of other molecular species. Contribute to the understanding of lunar volatile reservoirs and their interrelations, and observe the release of volatiles as a result of robotic interactions with the lunar environment. And there's a recent paper in Frontiers where you can find more information about the PROSPECT development. Then the one spectrometer that has already flown at the beginning of this year is the instrument that we provided as part of PITMS. There, obviously, we knew that the ECLIPSE missions are a comparatively risky way to go to the moon in comparison to traditional science missions. Because of that, we basically modified our development approach, and we went for a more technology demonstration point of approach and to a fast track development. So this instrument has been developed in only 1.5 years, which is, I think, very fast for our agency. The instrument has been developed and integrated with NASA-provided PITMS hardware, then qualified, calibrated, and delivered to GSFC in 2021. It has been integrated on the astrobotic lander in 22 and then launched earlier this year. Again, here we had a talk this morning by Barbara on the scientific results or measurement results of the mission, so I'm not going to talk much more about that aspect. But on the overall success for this instrument development, I can say that because we got an instrument operations time in orbit of 8.5 hours, and during that time, we basically were able to operate and to execute all the key functions of the instrument, even including the aperture cover of the wrapper provided by GSFC, and doing measurement with open and closed cover, exercising the software, even applying a software patch. So all of that worked well. So we can say that the technology demonstration aspect of the instrument was very successful. Obviously, it wasn't that successful as a lunar mission because we ended up in the Pacific and not on the moon. But again, the engineering was solid, and we were very happy to see that. Because of the risky approach of the CLIPS missions, on the agency side, we had expected the probability of success of the overall mission probably below 50%. And therefore, we went for this technology demonstration approach, where we have set our success criteria such that most of them had been completed actually before a lunar landing attempt. And that led to a success rate of about 90% for us on this mission. And that, I think, is something that we can be quite happy with. So the next incarnation of the instrument, and in many ways, I think this is the most exciting mission that we have embarked on so far, is a mission with JAXA and ISRO. The LUPEX mission is basically one where JAXA provides a lunar rover and a launcher, and ISRO provides the lander. There are payloads on both the lander and the rover from JAXA, ISRO, but also from us and from the United States. The rover mass it's quite a beast. It's 350 kilograms, and the lifetime is about 3.5 months. That's the baseline, with the possibility to extend it in terms of if it's possible to survive at least brief lunar nights. The launch is envisaged not earlier than 2026, and realistically speaking, we expect probably something in 27. It's launched on an JAXA launcher, the H3, and the rover is built by Mitsubishi Heavy Industries. ESA had proposed a number of candidate instruments for that mission, and JAXA has selected EMS as their preferred payload, and we are accommodated on the rover. So in terms of improvements over previous instrument builds, I think there's quite a number of them. We aim for higher cleanliness and lower noise levels in comparison to previous instrument incarnations. We integrate an in-situ calibration unit, basically a small unit with a gas reservoir of a calibration gas that occasionally gives a small puff of this calibration gas into the interior where the sensor is sitting. That allows us to very precisely calibrate the mass spectra. We aim for higher quality for Triple E components and software. And we designed the instrument for a longer lifetime than EMS CLIPS or also PROSPER, who have only one lunar day, while here we are aiming at least 3.5 lunar days and maybe more. Further, we strive for lower mass. We expect an instrument mass in the ballpark of 2.5 kilograms altogether, including a deployable cover or redeployable cover, a motorized cover. And we also have an integrated optical or thermal field of view sensor that tells us about the environment that our aperture is basically, or that our sensor is basically seeing. And of course, the best thing of all is provided by JAXA. We have mobility, which means that we're not only sitting on the lander and basically measuring the exosphere and measuring what the outgassing of the lander, but we are moving through the lunar landscape in sunlit areas. We're going into shadows, even in permanently shadowed areas. The JAXA rover has a drill on board, so it's going to drill. And our spectrometer will basically witness all these activities, including the robotic interaction with the lunar environment, and doing measurements along the mission with relatively high frequency. So you can see also, again, on the right side, the industrial consortium, this time led by Kaiser Italia, who are coordinating the contributions from the subcontractors, RAL Space and Open University, who have been on previous incarnations. So the heritage is basically preserved to a high degree. And then we have Oxford University and COMAT also in the consortium. Here you can see what the baseline planning is. So JAXA plans to land in a safe area that meets the landing criteria of the ISRO lander, and that provides a long duration of sunlight at the time of landing. Then the idea is to move along sunlit areas, and from there basically make excursions into permanently shadowed areas or transiently shadowed areas, do measurements there, drill there, use the ground penetrating radar and the other instruments that are on board, and basically collect scientific information before returning back to a safe space to recharge the batteries. So I think this is certainly the most exciting mission that we're embarking this instrument type on so far. We are quite advanced already in the development. We have started the industrial contract. We had already last week a meeting at JAXA for interface consolidation. We are expecting delivery of the first two models, a structural model and an engineering test model, by next year. And the year after, in 2026, we expect to deliver the flight model, and that is then followed by the preparation for the actual mission. So to wrap that up, based on the know-how of our industrial partners, a series of ITMS-based instruments has been developed, and one more is under development for JAXA. The capabilities have been successfully demonstrated in orbit. So we have TL9 achieved on the astrobotic mission, and PROSPECT will use parts of the design that we have flown on astrobotic 1 with PITMS. The latest version of EMS is a self-standing instrument with a deployable cover that is much improved in comparison to previous incarnations and is expected to deliver excellent data. So we expect this type of instrument to remain at the center of future lunar exploration efforts, and therefore we are investing in this line of development. And we have a contractual option for a second flight model of the EMS-LUPEX version of the instrument, in order to be able to react quickly to future flight opportunities that might pop up. So in case you have an exciting mission coming on, especially if it's a rover or hopper mission, I think we might be very interested. So please let us know. And I think that's all. Thank you very much. And I'm happy to answer any questions you might have.
Thank you, great. It's perfect time. So maybe we have 2 or 3 questions. Anyone has interesting questions? I may have some dumb questions. Just wondering, maybe it's depending on the instruments, but normally in general, how much it costs for the development, for full development for each instrument, and how long it takes?
It's a very good question, and the answer is difficult. And the reason for that is it depends on the one hand on the quality level that you want to achieve, and on the number of models that you need to develop. Typically, each model takes at least something like 8 months. So if you have 3 models to deliver, automatically you are probably in a ballpark of 3 years and maybe more. If you go for only a protoflight model, like what we did for PITMS, then 1.5 years is, as we have shown, is possible, but it's very sportive, and the team was sometimes on the edge of, maybe not a burnout, but serious overload. So I think for a PFM development, a healthy time frame is probably in the ballpark of 2 years. And then if you add to that 8 months for any extra model, for an instrument of that type of complexity, that is probably a reasonable assumption.